Okay, now let's talk about gravity's effect on fluid pressure. So if you have a cylinder filled of liquid, how will gravity affect it? So if first of all, in order to look at it, let's draw a free body diagram of the cylinder. So if this is the cylinder, the pressure that's being applied from the bottom is the same as the pressure that's being applied up. So this pressure is going to be most likely the atmospheric pressure, and this is the weight of the fluid in the cylinder. So first of all, let's apply Newton's second law to the cylinder. We will have sigma F, which is the sum of the forces, is equals to the force that's applied upwards, which is P2A, minus force that's applied downwards, P1A, minus the weight acting on it is 0. And the total is going to be 0. So now let's do P2 minus P1 minus mg, where m is going to be in terms of density, rho AD, g equals to 0. Rearranging all of these in order to get P2 equals P1 plus rho GD. What does that mean? If P1 is the pressure at the top of the cylinder is known, then the above expression can be used to find the variation of pressure with depth within the fluid. Okay, now what I want to talk about a little bit is how we put the W as rho AD. Okay, so this is very subtle, but it's very, very important for us to understand. So we know that weight equals mg. In terms of density, we express density as rho. Density is mass per unit volume of anything that you want. Okay, so this is density. I want to replace mass, so m is going to be rho v. Okay, in general, for most cases, if I was to consider this, for example, in here, the thing to be a cylinder. So the cylinder is going to look like this. It's going to have a particular area and a particular height. So I'm going to call this H. I think in there we call it D. Okay, so I'm just going to call it D. Okay, so that means it's going to be rho. Volume is area times D, which is the depth, equals m. So m can always be written as rho AD, as we did in that expression over there. So now note very carefully, this is going to be P2 equals P1 plus rho GD. Okay, so in other words, if the top of the fluid column is placed at the surface of the fluid, then P1 will be the atmospheric pressure if the container is left open. Right? So atmospheric pressure, we already talked about this. What is this? 1 atm at sea level, right? Okay, now let's look at an example. At the surface of a freshwater lake, the pressure is 105 kilopascal. What is the pressure increase in going 35 meters below the surface? Here, they are saying that on a surface of a freshwater lake, the pressure is going to be 105 kilopascals. What is the pressure increase in going 35 meters below the surface? So the depth they're giving me is 35 meters below the surface. So if this is my freshwater lake, I am going 35 meters below the surface, and this is what my P naught is. Okay? So that means I am looking for delta P. Right? How much is my pressure change from this point going in towards what I want? Okay, so that means I can use my equation P equals P naught plus rho GD. P minus P naught will be equals to rho GD. That means delta P will be equals to rho. For fresh water, the rho is going to be 100 kilograms per meter cubed. G is going to be 9.8 meters per second squared. And D is given, which is going to be 35 meters. Okay, so in this case, delta P, which is the change, is going to be 343 pascals. Now, it's very difficult to see what it actually means in pascals, so what I would recommend is you give your answer in atmospheric pressure And you know how to convert it into atmosphere, right? So I'm just going to do it, but you guys have to do it by hand, which means this is about 3.39 atmospheres. So you have, by just going 35 meters down the surface, you have increased about 4 atmospheric pressure. So your lungs and your body is now subjected to about 4 atmospheric pressures at just the depth of 35 meters. Another very interesting question. The surface pressure on planet Venus is 95 atmospheres. How far below the surface of the ocean on the Earth do you need to be to experience the same pressure? The density of seawater is 1025 kilograms per meter cubed. Here, they're saying that the surface pressure on Venus is 95, so the surface pressure is 95 atmospheres, right? How far below the ocean do we have to go to get the same surface pressure here on Earth? Where rho of the seawater that they give us is given as 1025 kilograms per meter cubed. Okay, so this is our problem. What do we know? We know P equals P naught plus rho G D. We need to find D, right? G is given, rho is given, and P naughts are given. But note these P naughts, this is going to be 1 atmosphere, and this is going to be 95 atmosphere because that's what we're looking for. So 95 minus 1 atmosphere is about 94 atmospheres, which is equals to rho GD. However, you cannot use atmospheres in order to calculate stuff. So what you need to do is convert this atmosphere into pascals. So you'll do the opposite of what we did before. So 1 atmospheric pressure is equals 1.013 times 10 to the 5 pascals. So this means 94 atmospheric pressure should be 94 times 1.013 times 10 to the 5 pascals, right? So you're going to plug that value in here. You are given rho, you are given G. Can you calculate D? And the answer is absolutely you can calculate D. So D comes out to be, for me, 948 meters, which is very close to about 1 kilometer, which is like 0.6 of a mile. So you have to go about 0.6 of a mile just to see how much pressure there is on the surface of Venus. And remember, we calculated that if you go 35 meters, the atmospheric pressure increases in the last example, that the atmospheric pressure actually increases 4 times. Okay, so keep all of those things sort of in your mind.